Good morning, everyone. This morning we will have 4 presentations. It's a pleasure to introduce your first presentation, generalized spectral bounds for quasi-twisted codes of Bucket Oskaya from Middle East Technical University. Thank you.
Thank you. Thanks for the introduction. Oh, thanks. Okay, thank you very much. So, good morning to all of you, and I would like to thank the organizers for this nice event. Due to the limited time, I will directly start by saying that today I'm going to introduce you the best performing minimum distance bound on the quasi-cyclic and quasi-twisted code families. Okay, it is best performing, but it comes with a huge computational price. So it is actually about this sequel of papers. The first one studies the single layer spectral bound for the quasi-twisted codes. And the second one is the first paper about the multi-layer construction of spectral bounds for quasi-cyclic codes. And I have been thinking since a while whether there is a more simple proof for all of this in a matter. Is a multiplication constant lambda is non-zero element of the finite field. So instead of seeing the code bursts as n times l arrays, where l is the index, I can introduce this notation, this array notation of code words, which is useful to understand the algebraic description of quasi-twisted codes. So basically, the lambda constant shift by l positions is equivalent to the row constant shift, where you take the bottom row to the top and multiply with lambda. In this description, I can simply say that, okay, every column is closed under lambda constant shift. Hence, you can map each column into a polynomial in this quotient ring R, where R is Fq(x) modulo x to the minus lambda. So simply you get an L tuple of polynomials of limited degree, and the row constant shift becomes multiplication by x at each coordinate. So since you are close under multiplication by x, you become an R submodule in R to the L. Using this structure, several algebraic properties of quasi-twisted and quasi-cyclic codes are investigated. So quasi-cyclic code simply means lambda equals 1 or q equals 2. Using this description, Lally and Fitzpatrick managed to give a Grobner basis for the given quasi-twisted code once we know the generators. Simply we think about this natural embedding from polynomial ring to the power L into R to the L, where the map is very natural. You simply take modulo x to the n minus lambda. So the pre-image of a given quasi-twisted code in RTDL, let's call this tilde, it must contain this basis set k tilde, which is simply xdl minus lambda times the standard basis vectors. So if you collect the generators of my quasi-twisted codes, let's say they have p of them, merge it with k tilde, then you can construct this matrix G by simply setting the basis vectors first as the first rows, and then x to the n minus lambda times the identity matrix, and then apply elementary row operations, but you shouldn't forget that you are working over the ring, so inverses might not exist. But in the end, you can obtain such an upper triangular matrix where the diagonal elements are divisors of x to the n minus lambda, and every element above the diagonal has degree less than the diagonal element, etc. So this is a Grosvenor basis, reduced Grosvenor basis in position over term order. So using this uniquely determined Grosvenor basis, you can describe your quasi-twisted code. So let's give the meaning of spectral to the word. So we consider the determinant of this polynomial matrix, which is simply the multiplication of diagonal elements, and the roots of this determinant are called the eigenvalues of the quasi-twisted code. So they are all nth roots of lambda, of course. And then eigenspace definition is natural, so you simply evaluate at the eigenvalue beta, and then you calculate the corresponding eigenspace of the scalar vector, but everything happens in some extension field, of course, wherever x to the n minus lambda splits. So let's say I have omega bar as my set of eigenvalues. Just like in the cyclic or constant cyclic case, if I have no zeros, no roots, then I have a full space code. That is natural. So I can simply say that the eigenvalues of quasi-cyclic or quasi-twisted codes are the analogs of zeros of cyclic or quasi-cyclic codes. So in the sense that using the zeros of cyclic or cyclic or constant cyclic codes, you can use defining set bounds, like VH bound, like Hartmann-Senk bound, other bounds. So the idea of Semenov and Trifonov was, in their paper in 2012, okay, we would like to present some BCH-like bound for constant cyclic codes. Everything started with that. So for that, you require some sort of roots, some sort of zeros of the given quasi-cyclic code or quasi-twisted code, and here they are, the eigenvalues. So what are we going to do with them is that we need one more linear notion, the so-called eigencode, which are the FQ duals of the eigenspaces. So the eigenvalues will behave like the zeros. On the other hand, there is some linear structure within every quasi-cyclic or twisted code, so that will be characterized by this eigencode. And after all this tiresome setup, finally we can state a single layer spectral bound as follows. That is from the first paper I mentioned at the beginning. So once I can collect all the eigenvalues, I can apply some defining set bound on it. It is up to your choice. It can be VCH bound, rows bound, shift bound, whatever you desire. But there will be a corresponding eigencode which you derive from the eigenspaces. That has to be in the scene as well. So, what do I know from the theory of cyclic codes is that, okay, if I involve more and more zeros, I can get a closer prescription of the minimum distance. So, that is to say, if P goes larger, then dP increases. But since I consider the intersection of the corresponding eigenspaces, where beta comes from P, their FQ dual will be a direct sum of eigencodes. So if you increase P, the number of elements in P, if the cardinality increases, then in the dual, the sum will increase as well, hence the minimum distance will drop. So there's a trade-off. As P increases, dP increases, but dCP decreases. So there has to be a balance. That's why it is not straightforward to run the computation for the bound even in the single layer case. So you can tell me, okay, Buket, but you have been in this algebraic coding business for more than a decade now, so what is the real challenge here? I would say that, okay, a naive approach would have been to think about the mid-size, right? So that everything sets into the balance, but it is not the case. So somewhere in the middle, let's say at the half of the eigenvalue set size, you get a nice estimation in terms of this defining set bound, but by adding just one more root, maybe you jump from BCH estimate to Hartmann-Senk estimate and you get a better prescription, but this DCP can fall dramatically. So there is no prescription in that. In that sense, okay, that sort of undeterministic behavior is very beautiful in the sense of code-based cryptography, because I mean you cannot simply set a behavior, how to say, a monotone behavior, just like in the cyclic or post-cyclic codes, because there is some linear factor here which affects everything. But in the, I mean, okay, they might be good for code-based crypto schemes, but if you try to determine the minimum distance, then huge efforts have been made, ending up with very complicated bounds, and which you need to introduce a lot of algebraic properties to understand the bound itself, which is not desirable as well. But anyway, so another idea was to generalize this spectral bound in the multi-layer setup. So instead of taking one subset P of eigenvalues, let's take S of them. So that was the second idea for the quasi-cyclic codes. So this long and ugly formula is for the multi-layer version. But it performs better than the other algebraic bounds like Jensen bound and the Lally bound, etc. Even to understand the Jensen bound itself, you have to understand another description, algebraic description of quasi-cyclic codes. It is not easy as well, and it is not easy to implement as well, and so is this one. But numerically, if you manage to keep the number of S and the number of defining set bounds used in a moderate number, then this really outperforms everything we know so far. So I will briefly go over the proof idea. So simply, you take that type of Vandermonde-like matrices, and then you take the Kronecker product of them with the corresponding eigenspaces. So if you remember the case in the cyclic code, so whenever you have roots of its generator polynomial, you can build the corresponding Vandermonde matrix, and you can use it as the parent-shaped matrix, right? So that simply means that every cyclic code has an ancestor at the extension field, Red-Solomon-like ancestor. So the cyclic code lives in the subfield as a subfield subgroup. So what Semenov and Trifonov try to do is to generalize this notion for the quasi-cyclic codes, actually. May I find some ancestor in the extension field whose parity check matrix can serve as a parity check matrix in the subfield as well? So they managed to do so, but this linearity sort of complicates things. So in the old paper that I showed, the middle one, uses a lot of coding theoretic techniques and a long case analysis to prove this fact. Then I have been thinking since a while, okay, I mean, if you set S equals 1, I mean, if you just think about one Kronecker product only, then you get the old spectral bound. I will go back to my slides showing the parity check matrix construction here. So simply, just like in the cyclicals, there is some sort of van der Waals structure here as well. But those eigenspaces should be involved as well. But in the end, I can say that, okay, once I have the eigenvalues and the corresponding eigenspaces, then I can construct the parity check matrix in the extension field where x to the n minus number split. And then I can build either a single layer bound or a multi-layer bound out of it. But the natural question is that which subsets to use? That really depends on the defining set bounds that you use or the computational resources you have. So I will go over the simplified version of the proof, which only uses one very well-known fact in coding theory. If I have a parity check matrix, then I look at the number of linearly independent columns to estimate the minimum distance. But I have some special structure there. I simply take some vertical join of Kronecker products. So I am wondering about the number of linearly independent columns when I take a vertical join and a Kronecker product. So this is the induction basis, which takes the special numbers NA and NB as the maximum number of independent columns. So in a sense that if I have two matrices with the same number of columns, then a linear combination of columns is determined by the higher number of independents. On the other hand, if I have a Kronecker product, then okay, I have to take the minimum. Because the Kronecker product can be viewed from two directions. Either the independence is determined by A or by B. If it can make an A dependent faster than an B, then okay, let's align the Kronecker product accordingly, and vice versa. So this is the basis of the inductive arguments, and as a corollary, you can get, just by using the second part, you can get the single layer spectral bound that I introduced you at the beginning. But in order to generalize this, we need this proposition and this huge number. So I am trying to determine the number of independent columns of this more generalized version. The proof is a technical induction, but still simpler than the previous versions. So the spectral bound, the generalized spectral bound, follows as a corollary of this proposition. And the nice thing, for me at least, the nice thing is that, okay, it only uses linear algebra in the proof, and you just count the maximum number of independent columns, and you build your spectral bound accordingly. So instead of A's, you can put P's, and then those B's will become the eigenspaces. So you can use this structure. But, okay, a nice way to understanding this bound. And here comes the computation. Since there is no monotonic behavior in the defining set bound side and the eigencode distance side, first of all, for each choice of an S tuple, even if S is equal to 0, I have this exponential number for comparison. So if I consider the cardinality of the eigenvalue set, let's call this T, then I have to consider 2 to the T minus 1 non-empty subset. Just because of this increasing, decreasing behavior. And I have to do it S times if I consider the multi-layer version. That is the first obstacle. Then the types of defining set bounds considered has a tremendous effect as well. I mean, naturally, you might want to evoke as many defining set bounds as there are. For my computational purposes, I only use four, the BCH bound, Hartmann-Senk bound, the Ross bound, and the minimum distance of the code at the extension field, which is also a lower bound on the code. Only four types, but even that increases a lot, because for each member in this S tuple, you use K estimates. So in total, this number increases tremendously. As I said before, I mean, you might say that, okay, maybe there has to be some sort of elimination process in the computation, but as I said, it is not easy. I mean, adding some roots or extracting some roots can have a really unpredictable effect on the linear side. So that's why I computed brute force. And as a result, the simulations could be run over 135 randomized codes only in 2 weeks. That is very bad, because K is equal to 4, and I tried my best to keep the eigenvalue set size manageable, but still, I would say this is a very bad, very, very bad simulation. But still, I can conclude that, okay, if I consider just 2 subsets, 3 subsets, or 4 subsets, this is the estimate of the Jensen bound, which also takes its time to calculate, and the old spectral bound, I can say that, okay, it is the best performing one. And it gives the minimum distance in the sharp way much more than the others. But in order to derive statistics, this number is too small. This number is too small. Maybe, I mean, I should run a computer for months and months to derive more healthy results. Okay, and I would like to thank for your attention.
Thank you very much for your talk. Any comments or questions? Let's take your Speaker, Daniel Planario from Carleton University. The title is Cycle Structure of Feedback Linearly Extended Discrete Functions.
Thank you. Okay, thank you. So I should say, instead of leaving it for the last slide, I would say at the beginning, this is John work with Claude Gravel is there, and Hugo Teixeira was my student, my PhD student in Ottawa. Okay, so this topic or this talk is about composition of functions. And this is an area that actually, although there is a lot of work nowadays related to finite fields, it's an area that existed a lot on finite groups and linear maps and so on. Indeed, many work on linearity was done already in the 60s in biology, because they could model certain, it's actually over F2, they were Boolean functions that they were modeling. But in the 70s, there was a big explosion because of polar row algorithm for integer factorization, and then especially discrete log computations. So through that, they iterate the function, a quadratic function. So you want to know what happened with the composition of a quadratic function. And so that was the general area. Now sometimes it's called dynamical system over finite fields. There is dynamical system also over other finite groups and so on. And in this particular case, we'll be interested on some particular transformation that I'll explain in a minute. So here's an example. You grab a function, for example, x to the 5 plus 2 in f5 squared, and it turns out that when you plot it, you can look at the actual points. They always have one ahead because it's like a function, right? But on the other hand, they may have many values whose image is that point. In this case, it's not, it's a permutation. And this is here it is. Somehow it's keeping the definition. So here is the actual definition. It's very, very simple. You grab a finite field, and you create the vertices of a graph, are your elements in the finite field, and then you have an edge to the next value is the function of the value of the function on x. F of x equal to y, you have an edge x to y. And then because of the finiteness of that you are working, the finite group or finite fixed finite subset, it turns out that you will cycle back. So there will be some minimum L and M there, such that for any point that you pick, A, yeah, you start applying F, you compose, and eventually you come back. In this case, M iteration. So you will say that you have a cycle of length N. And because of this nature of this, you will, of the finiteness, you will always have this return. Okay? And then if you have a cycle, the points are called cyclic or periodic. The other ones are called pre-periodic or transient. They have other names. They will not matter to us because we'll be talking about permutations. So they will not exist in this topic. Okay, so this was the example. Here are there are tons of citations that I could do here, and I really mean in the order of hundreds. But so this is kind of basic here. The first one is important to us. There is another one that I'm not citing here in the 90s too that will be important to us because we will be dealing with some linear transformations here. And then I just want to point out that there was some interest on the. Oops, I present something weird here. So after those things in the 70s, as I said, there was polar algorithm. So a lot of people got interested on dealing with quadratic functions. What happened with the iterations of quadratic functions? Then obviously you can generalize to any monomial because this was x squared was quite important. X squared minus 2 was also very important. It's a Chebyshev polynomial. So those two cases were very important, and many others. And then eventually you do the x cube, and then you generalize to other functions and so on, and there are many more works. There are also works outside the finite fields in more general settings, like this work of Alexander Bors on dynamics of endomorphism in finite groups in general, Dedekind domain by Claudia and Lucas. And I just want to point out that we have a recent paper, it's appeared in the memoirs of the European Mathematical Society in Europe, on the dynamics of something called the analysis of atomic mappings, but I won't talk about that today. If you're interested in this, you never hear about this topic, there is a possibility in any room. Let me just say that here is a survey that we wrote with Rodrigo and Claudio, and I can give you the link later. I think it's the best point to start. It really has a lot of connections here. And 150 citations already. Okay, so what are we interested here? We are interested in the case of this feedback linearly extended discrete function. So what is that? Is this. So you will get an nm integers, you get these vector spaces over Q, dimensions n, m, n minus m, and then these transformations, or I will be using matrices too, but anyway, so these are full rank matrices on the respective places here, and then you have this connection here. So your transformation is called f, receives an x in fqn, and will return a value in fqn. So your little f here in blue doesn't have necessarily the same dimensions, thank you very much, but in this case here, you are from fqn to fqn. And here is the transformation. You get an x, you sum bt, we transpose fax, and then you apply the function t. And at the end of the story, that's your f of x. It turns out that, okay, the first question is, why? Yeah, I'll tell you why in one slide, and I move on later, but because you can think of, come on, I can create other things, right? Why this one, right? Obviously, you can have that question, but I'll try to motivate it in one slide. Now, it turns out that this was done in a paper with Claude, and it turns out that we showed that this function here, you will always be a permutation. So that means that that's kind of interesting now because it's permutation polynomials, right? So so now what we want to say in this paper is we want to talk about in this paper is about the characterization of how the function decomposed into samples. And for that, we will do this composition of functions. We take a look at the graph, and we will prove theorems about the structure of those cycles, how many cycles of this size you have. And okay, so why? Well, turns out there is a relation to cryptography that we explained in the first paper, in the 2023 paper, where we go on in a section showing that these actually are particular examples of very, very well-known ciphers in cryptography. And in another paper, 2024, we just proved some cryptographical important properties against attacks that you can have. So that's the motivation, and that's why that f, let me rewrite the f here, rewrite in the slide. Okay, so we will be grabbing an x, we will add in this bt fax, and then we will apply a t, and that's our function. Okay, so I will start by realizing one thing. This can get out of hand very quickly, right? Because you have a lot of variation here. Your ABT will satisfy some condition, A, B transpose being 0. That is important for the permutation property of this, but that's not so important here. Look at here. I have a lot of variation on the little f, and I have a lot of variation on the capital T. And that gets that you cannot expect to produce a general result for all those cases, at least not on the first work on this. So what we will be doing is getting some particular values here. The first case that we did is pick that the T is the identity. Turns out that this trivializes things quickly, and it gets very easier in a way. But when T is general and your F starts getting sort of a small values, then already you start seeing a lot of different variation. So if your T is identity, of course you don't have this. So your function is grab an X and apply this. You know that BTA is 0, but there is an F here in the middle, right? And the F could be whatever, any. So anyway, it turns out that you studied this, it's not very difficult, and you show that the only cycles possible are of length 1 and p, and actually you can say how many fixed points are there. If you have a cycle of length 1 equal a fixed point, so there are this number of fixed points, and the others are in cycles of length p. It involves some proof, but it's not very difficult. So the interesting case is, okay, I am like Sarah here, jumping ahead of myself. The other thing is that you may say, okay, but I could change the function every way I go. So every iteration f1, you use a little f1 that will give you a capital F1 by this transformation, and you do different j's here also. And now you do the composition not of the same f, but different f's, because different capital f's, because the little f's are different. You can do that and solve that. The structure is basically the same. The difference is the function. The function is the sum of the function. It's a small difference that doesn't change a lot of the structure. So it's not so difficult anyway. Now, the case of interest, I don't know why this jumps so fast. It's very hard, yeah. Yeah. So if the t is non-trivial, if the t is non-trivial, then okay, now you have a generic t. Now you need to play with a little f. And the first thing we did, and it already became quite what you will see in the next slide, is the fixing all the functions. Let's say you have only one function, not many functions, and you fix it to c. Doesn't matter if you put many constant, different fj, a different constant y there, it doesn't really matter. It gets the same structure, more complicated, but the structure will be sort of similar. And in this case, you do some very basic counting, and you realize that your function is actually like this. So it's an affine there transformation. There you have your x, you need to add a constant. The constant is not this one, is b transpose y. That doesn't matter, it's a constant. And in this case, if you iterate it L times, you get the iteration of the x, and then the summations of the c's. You see, these are the t applies in the c's for every guy up to L that you have there. So, first case, and the only one that I would likely present today, is T is a diagonalizable transformation. In the slides, you have also how things complicate a bit when it's non-diagonalizable, when you have multiples f. It's just a small complications as you go. So the T is a diagonalizable transformation. So we have some shape. T can be written as PDP inverse. This is linear algebra 1. So D is a diagonal matrix that contains eigenvalues. Eigenvalues live in the algebraic closure there of Fq. And your transformation is T of x plus C equal to x for some C. You can vary the C if you want. So you do basic things, and you realize immediately that if 1 is an eigenvalue here, then something will happen. And if 1 is not an eigenvalue, something else. 1 plays a role here, because here you have a 0, right? So then it turns out that if 1 is not an eigenvalue, it's immediate or quick to realize that it's a unique fixed point. But when 1 is an eigenvalue, then things change. If your C does not belong to the column, you see it here, if your C does not belong to the column of T minus I, then you have no fixed points, but if it is, you have Q to the algebraic multiplicity, the multiplicity, how many times the eigenvalue E1 appears. And this sort of start complicated from here, what will be happening, right? So the first thing you realize is, okay, I need to find this result, because if you remember your x, right? You are in a cycle of length j. If after j iterations you have this point, you come back to x, right? So this is actually the application of your function j times. I showed it a few slides ago. And you want it to be equal to x, that is to say to return to x. So you have this cycle. And from here you have this expression. This shows you that there is a minimal d when this summation here will be up to d here, is already in the column. And that minimal d is quite crucial because that's the part of the you need to prove. All the cycles have multiple lengths, multiple of d. So that d here, in the moment that you detect the d, you know the possibility of the cycles are multiples of d. So from there, you can actually count how many cycles of length d times j is a multiple of j of d. So let's say it's the multiple is j, right? So the number of elements that you have in dj is a classical inclusion-exclusion for combinatorics. The only interesting part here on the exponent of the q is not the multiplicity as before, but it's this expression here where you sum over the divisors of your j here, of the eigenvalues. That's the result. the summation here runs over certain di's, which are the di's, are the orders of the eigenvalues. So you now are in the realm of very much linear algebra, eigenvalues, and so on, and you can get immediately a number of cycles just like this. Okay, can we say more? Yes, we can say exactly which are the more possible cycle lengths. Yes, they are multiples of d, but actually it's the least common multiple of d with s. S is any subset of the orders of the eigenvalues that you have. So there is this d again, this minimal d, such that this expression is in the column. All are multiples of those d. Which multiple? Well, LCM of s and d, where s runs over small subsets of the distinct orders of the eigenvalues that you have. So this allows you to play a bit, to control a bit, the number of cycles that you want. Turns out that in this area of block cipher, it's known that, for example, it's not good to have this permutation, it's not good to have many fixed points. So you can play with this to have very few points or whatever you want. If you want to have a complete cycle, you can play with this and try to control the sizes of the cycles. For example, here I write something about, if you want to maximize the cycles, you can hit 2 to the n and it's a plain. So here's an example. So let's say my q is 9, my n is 3, so I'm 9 to the 3, and let's say my t is something like this. So let's say I simplify myself here. So these will be your eigenvalues here, alpha square, and 1. Let's say your C is 001, you compute TC, you compute T square C, it's null in the column of T square I, you compute T cube, T square C, TC, bingo, it is. So these three, all the cycles are multiples of 3 for these guys here. Moreover, you can apply the theorems and do some elementary number theory with Morris functions and summations over divisors of the multiplicities, and you compute and you get the exact number. So you have 3 cycles, because you have 9 elements in cycles of length 3. You have 3 cycles of length 3, etc. 6 of length 12 and a huge amount of 24s, and you can plot it, and you can find them. Here you have a blue of 3, here you have a blue of 3, a blue of 3. Those are the cycles of length 3, and etc. The 6 are in green, and all the other. So, okay, now I need to check. When I finish your cycle? Oh, 15. All right, so I will tell you, I have like 3 minutes, so I will tell you very briefly how these theorems change for non-diagonalizable and several functions. Okay, so non-diagonalizable, what are the changes? Well, we will be using Jordan, matrices, Jordan forms, and so on. Turns out that, again, I jumped at 1. So this is we will be using these blocks. You have the eigenvalue and you have the ones on the diagonal, upper diagonal. And you have blocks of this in the Jordan normal form, and you have your T is Pj P inverse, right? Okay. All right. It's magic how I can do. Okay. So the result for the number of elements in the cycles of length multiple of d. The multiple of d here is called k. Well, what it changes here at the top. Instead of having the summation of the multiplicity, you need to compute the nullity, the dimension of the kernel of j to the to di. The i's are the divisors of the k, and the di and the d is certain d here, the minimal, etc. as before. Okay, so that means that you need to compute the kernel of this t to the I minus I. Turns out that the t to the I minus I you computed is this matrix here, where some binomial numbers start appearing here. Lambda is the eigenvalue that you have, and this is the computation. You need the kernel of it, the dimension of the kernel of it. Turns out that for that, you see the binomials. I'm connected to the previous talk. Of course, we will be using Lucas theorem, because it's what you do when you have binomials on T. And actually, from there, you can compute the nullity. The nullity involves the periodic evaluation that also appeared in the slide, right? Although she didn't say it. So, so you have the nullity now, and the nullity depends on the I power here, j to the I power, the order of the alpha, the order of the lambda, sorry, the eigenvalue, dividing or not dividing. That's the proposition, and from there you can now compute. Let's skip the first one here. We go directly to the final one. you can say which are the only possible cycle lengths. The only possible cycle lengths are one, an LCM, SD as before, S is as before, you see D here, the delta, the S is a subset here, the little d is the same little d, the minimal that's the dimension of the TIC is in the column of T to the minus T to the D minus I, but now you have a P to the N, in addition here, in the LCM, and this comes because the possible orders are not anymore P. They become D order of alpha and P to the N, where n range this. Your R here that you need here, your R here, is the first value that P to the R is bigger than N, right? So, for example, if you have one single Jordan block, you see the one single, you see one single Jordan block, you can compute the number, you have one, in this example, you have one cycle fixed point, well, 2 or 4 because they have 8 and so on, and you can plot it, and somewhere there is your orange alone. The 4s are one around here in the middle and one around here. I know because I checked it today, but it's difficult to check because of the blue and the green and too close. Yeah, if you have 2 Jordan blocks, is like here you have 2 Jordan blocks. You see, it's a little bit more computation. Okay, and I am.
Any question or comment? You have more time to.
You see what happens when you don't ask questions. Just if you do the multiple, so you change the C. If you change the C's, so now you are doing T of X plus Ci, you can now have different F's, right? And you do the computation. The expression get a little bit more complicated than before, but it's very similar, so the result is very similar. Instead of having one nullity, you have a summation of nullities, kind of expected. Think for some minutes. And then you can get your, not Q to the minimum, whatever, but you get the Q to the summation. So small changes, you see, small changes. And basically the same thing. The GCD gets a little more complicated. So the LCM is not anymore just SDPM you need to. So this gets a little bit more involved at the end. But in the end, you can do the same things. You can plug your Qs, your Ns, different Cs here. You compute your D, in this example will be 2, and you can compute it. And the overall question is now, how can you do more than this? I believe we can do, instead of C's, linear expressions in the F inside with general capital T, and maybe otherwise exploit relations between A and B.
Thank you. Let's thank your speaker. Henry Caraballo,
That's my point.
from Middle East Technical University. The title is Extended FP-bound for LCD codes and New Binary and Ternary LCD codes.
Okay, hello everyone. I'm going to speak about the linear programming bound today, and we generated some novel, I would say, binary and ternary codes. So here's the outline. I will briefly introduce some of the notions, then I will continue with the linear programming bound for the LCD codes, then I will present some new methods, extended methods, new methods for the linear algebraic construction of the LCD codes. Then I will continue with the cyclic and quasi-cyclic LCD code generation. So as an introduction, LCD codes are actually intersect with their dual trivially, and they are first introduced by Massey in 1992. They are widely used by for a dual masking scheme to defend against the side channel attacks, and it's known that for the values of Q greater than 3, every linear code is equivalent to the LCD code. This is proven by Carlet et al. And so, but for binary and ternary codes, it is still relevant to study those codes. So our research is focused on type bounds and explicit construction over FQ. What we're trying to improve in this research is basically our goal was to create some kind of LCD pool as much as possible, and we try to get rid of the non-LCD codes. So we try to introduce you the novel LCD codes as much as possible. Then we compile up to some bounds for binary cases up to 60, for ternary cases up to 50. Then we introduce some novel algebraic construction. Basically, the idea was to generate some stopping bound for our research algorithm. Then using that bound, we actually brute force research through some LCD codes using the other LCD codes. Then using this factorization method, we generated some cyclic and quasi-cyclic codes and computed their minimum distances. Well, in a difference, I would say we wrote all our codes in Python, and it can be found in our GitHub repository. For preliminaries, I can say that this is the Massey's LCD code, and this is the characterization of the usual LCD code, and this is the permission version of the LCD code, which is presented in the Güney, Özkaya, and Sola paper. This is the Cauchy polynomial, and this is how is it used in the Macmillan identities. We're going to use this Macmillan identities to introduce another constraint on the linear programming bound. This is the well-known Del-Sartes linear programming bound, and it tries to maximize the summation of the weight distribution, and this is this optimization problem is subject to this following condition. I would say the improved LCD linear programming bound is using, introducing another, like the third constraint here, using the Macmillan identities to force this bound to be LCD bound. This is improved version, I would say, and this is using the fact that up to the d-1 minimum weight of the coefficients of the weight distribution is 0. So we are using that fact to generate new constraint. This is actually improving the LCD linear programming bound. So but since this is an optimization problem, we can't blindly use these bounds. We compare these results with the known bounds in our program. So first we use the singleton bound, Hamming bound, Polkin bound, Elias bound, and for the lower bound, of course, we use the Larson lower bound. Then we went to construct the acidic codes out of known acidic codes for. Then we basically employed new algebraic construction methods because we needed some methods to generate new acidic codes out of acidic codes. So if I continue, this is the first method I can introduce. This is a lemma coming from Voyukeleva's 2021 paper. So basically, it was the Voyukeleva made this lemma for binary, but we proved that it's also working for the ternary cases. And there was another proposition in that paper. Basically, we extend this proposition and prove that it's working for the FQ cases. In the 2021 paper of Harada, there was a theorem to 3.1, and we named that theorem as extended construction method 1. Basically, it allows you to generate, given an LCD code, it allows you to generate n plus r k plus 1. In Harada's paper, it was n plus p. Proof comes from the matrix characterization. If you multiply the generated matrix with transposition carefully, you can obtain the conditions and the proof. If you continue, we needed another sort of method to increase maybe k plus n cases. So we found another construction method, basically from the Lees et al. Paper, which is it was from 2024, so pretty much recent paper. If you look at this method, it allows you to generate n plus r, k plus n LCD codes out of LCD codes. There was another corollary of this the theorem. It allows you to generate, basically, it allows you to extend the dimension of the code. But we couldn't, if you want to generate new LCD codes out of LCD codes, you can use this method, but there are some caveats. Basically, you have to know how these methods are actually affecting the minimum weights of the newly generated code. So we try to study the likelihood of effect of these methods, and after this study, we went ahead and created an algorithm of these to generate these new codes. So basically, we split our algorithm to enhance the given code for targets specific. For example, nk parameters. Then we put that newly generated code into queue. Then we brute force the search through the space. For example, after finding those codes, we put it into some nicely created JSON structure. For example, if you look at here, the key of this JSON file is composed of the Q, N, K, and the maximum possible minimum weight. If you look at this example, for example, this code is 4823. It is generated from 4622, and it is also generated from 41 and 21 code. So this is the generator message of this code, and this example, for example, from this parent code, you can create this code using the extended construction method 1. And this is the parameter object that you need to use. For algebraic construction of the cyclic codes, we use the Yang and Messey's paper in 1994. They presented that theorem, and we used that theorem to basically split up this n to the x to the n minus 1 into this self-reciprocal and reciprocal pair. Then we created some subset of F and E, and if you use the union of this subset, you can basically create any self-reciprocal LCD codes out of this newly created subset. So for quasi-cyclic code, it is a bit tricky. You have to understand the composition of the cyclic code. but it's again starting from the factorization of x to the n minus x to the n minus 1. Then you basically create self-reciprocal, reciprocal pair. Then you have to continue with the CRT decomposition of this factorization. Then you need to define a map. Then that map is naturally decomposes over alpha plus over r. Then basically you can see that you can see from here this quasi-cyclic code is generated by its constituents. So the idea is if you can create these constituents, you can create a quasi-cyclic LCD code. Then basically these constituents are spanned by these GIs. This is the theorem of the LCD quasi-cyclic conditions from Wiener et al. Paper. If you have a C that is, if you want to have a quasi-cyclic LCD code, the CI has to be either Hermitian or Euclidean LCD codes. Then there is other conditions on the Cj prime and Cj double prime. So we equip these GIs with appropriate inner products. Then we randomly generated this constituent codes and we combined them to obtain the quasi-cyclic LCD codes. This is so at this point I have to say thank you to Marcus Grassel for allowing us to use his magma functions to generate this quasi-cyclic LCD codes. This is going too fast. So this is the references. I would say that the references that we used in our paper was not that broad, but we try to use as much as possible, and we try to eliminate as much as possible while generating this new LCD code. So you can visit our GitHub repository to see the repository basically and look at the LCD codes. And that's
Any questions or comments? Let's thank our speaker again. Thank you all for attending this session.